Hi everyone, my name is Stephanie and I'm here today to teach you the basics of rational exponents and radical expressions. Let's start with rational exponents. Rational exponents are exponents expressed with any ratio of two integers where the denominator is not equal to 0. As you can see in this example, we have a to the 1 over nth power, where a is the base and 1 over n is the exponent, where n should not equal to 0 because it will be undefined. Moving on to simplifying expressions with rational exponents. The basic rule of thumb is if a is greater than 0 and n is a positive integer, the number a to the 1 over nth power is the number whose nth power is a. So what does this look like with numerical examples? Below here, we have 3 examples. If we take 9 to the half power, we get 3 because taking 3 to the nth power, which in our case is 2, will result in 9. Alternatively, simplifying expressions with rational exponents can be applied to any nth power, including 64 to the 1/3 power, or 4 cubed, and negative 32 to the 1/5 power, or negative 2 to the 5th power. There are 2 ways to evaluate radical exponent a to the m over nth power. One way is the nth root of a to the m power. The other way is taking the nth root of a and taking that to the mth power. Let's try this concept out by evaluating the same radical exponents in 2 ways. Here we have 25 to 3/2 power. First, we can take 25 to the half power, or square root of 25, and apply the 3rd power, which brings us to 5 to the 3rd power, or 125. Second, we can take 25 to the 3rd power and taking the square root, or half power. Going through the step-by-step, we can take the square root of 25 squared times the square root of 25, or 25 times 5, bringing us to 125. So what happens when we have an expression with a negative exponent? Here we have 32 to the negative 2/5 power. We can rewrite this as 32 to the 5th power and apply the negative 2/5 power to that. Using the product rule, we can combine the 5th and negative 2/5 power to get 2 negative squared. Now, we apply the negative exponent rule by rewriting the expression as 1 over 2 squared, or 1/4. Another example we can use is 16 to the negative 3/4 power. Again, we can rewrite 16 as 2 to the 4th power and apply the negative 3/4 power to that. Once we simplify the 2 exponents using the product rule, we get 2 to the negative 3rd power, or 1 over 2 to the third power. Ultimately simplified as 1/8. A good rule to note is that a negative exponent does not affect the sign of the number. Now let's explore expressions with variables. In this first example, we have b to the 1/2 power times b to the 2/3 power. To simplify, we can first find the common denominator for both powers, which is 6. Now we can rewrite both expressions as such. By applying the addition rule of exponents, since our bases are the same, we can add both exponents together. 3/6 plus 4/6 gets us 7/6. In this second example, we can separate the terms and apply the exponents separately. First, we can take the 1/2 power or square root of 16. Which comes to 4. Then we can apply the square root for the next two terms by using the product rule. And multiply both exponents of both terms, leaving us with x cubed and y squared. With the final solution, 4x cubed y squared. Moving on. So what happens when a is negative and n is an even number? Well, then a to the 1/nth power is actually not a real number. In this example, we have -9 to the 1/2 power equals x. By definition of a to the 1/nth power, x squared is -9. However, the square of any real number is not a negative number. Therefore, -9 to the 1/2 power is not a real number. Our next topic is on radical expressions. Radical expressions are any expressions containing a radical symbol, or this symbol right here. It's also known as the nth root of a. People often mistakenly call this a square root symbol, but it can also be used to describe a cube root, fourth root, or higher. The basic rule of thumb is that if a is a real number and n is a positive integer, then the nth root of a is also known as a to the 1/nth power. So let's break down what a radical expression really is. It is comprised of 3 components. The radical, which is this sign, the index of the radical, which is n, or the nth root, and a radicand, or the term in the radical. When we write rational exponents as a radical expression, assuming a to the 1nth power is a real number, then it is a to the m over nth power is equal to the nth root of a to the nth power. Let's go through some examples of how we can rewrite exponential expressions as a radical expression. First, we have 3x to the 2/3 power. We can identify the components of a radical expression by using what we have here. Using the a to the m over nth power rule, the index looks to be 3, and the radicand looks to be 3x to the 2nd power. So now we can rewrite this as the cubed root of 3x squared. To simplify this more, we can also write it as cube root of 9x squared. Let's do it again in the second example. Now, the 2/3 power rule is applied to the x. We can rewrite this as negative 2 times x squared to the 1/3 power, or negative 2 cube root of x squared. Now that we rewrote exponential expressions as radical expressions, we should go over how to go the other way, which is to rewrite radical expressions as exponential expressions. First example here, let's identify the index and the radicand. The index looks to be 7, and the radicand is x to the 5th power. So if we apply the a to the m over nth power rule, n is equal to 7 and m is equal to 5. Which brings us to x to the 5/7 power. The second example here, we have the cube root of a cubed plus b cubed. This equation is a single expression and should not be separated. As such, the index here is 3, and the radicand is a cubed plus b cubed. To rewrite our expression here, n is equal to 3 and m is equal to 1. Now we have a cubed plus b cubed to the 1/3 power. Now let's move on to the next topic, simplifying radical expressions that are roots of perfect powers. As a general rule of thumb, the value of nth root of a to the nth power depends on whether n is an odd or even positive integer. If it is an even integer, then we can write the solution of both of these radical expressions as either the positive or negative absolute value of a. Alternatively, if n is an odd integer, we can only write this expression that the nth root of a to the nth power is a. The reason being is that using cube root as an example, the cube root of a positive number is positive and the cube root of a negative number is negative. Therefore, we cannot assume that the solution of these perfect roots will always be positive or an absolute value. So what is a perfect power? Well, a perfect power is when a variable's expression's exponents on the factors are evenly divisible by the index of the radical. As an example, these are all perfect roots. You see how all of the solutions are a whole number? There's no approximation or decimals following the whole number. However, there is such a thing as an irrational number, which is a variable expression that is not a perfect power. Its root can only be approximated and their decimals will never terminate or repeat. Finally, let's practice applying perfect powers on these two examples. In this first example, we have the square root of 49x squared. Both terms here are perfect roots. The square root of 49 is 7. And the square root of x squared is x. Leaving us the perfect solution of 7x. In our second example, we have negative fourth root of 16a to the fourth power, b to the eighth power. All terms here are divisible perfectly by the root, which is 4. If we apply the fourth root to each of them, the fourth root of 16 is 2. Subsequently, using the quotient rule, the fourth root of a to the fourth is just a. And the fourth root of b to the eighth is b squared. With the final solution, 2ab squared. Well, that wraps up our topic today on rational exponents and radical expressions. Thank you so much for tuning in, and I hope this video has helped.